put on a blackboard the instruction of how to install PyQuil?
So you would go to this particular GitHub over here, and maybe Norm, you could share the link in the chat as well. So if you go to this GitHub, you could either download, I mean, you know, just git clone the repo, but also if you follow the README instructions, you can actually run the notebooks, or at least some of the notebooks in there through Google Colab. And for one of those, well, part of one of the exercises, the Trotter LCU, you would need to install PyQuil. Unfortunately, the way that PyQuil works, you can't actually run it on Google Colab because you need to run what's known as the quantum virtual machine, which is like a software that uses your laptop as sort of you know, a dummy quantum computer, sort of used as a server. And then there's the Quill compiler. All of those things need to be running on your laptop in server mode. So yes, so go to that GitHub page, the one that you see over there, github.com/n-tubman/collab summer school, and you should be able to see that. And then I guess if you scroll down, README, there should be a link to the actual collab. So here we have, like, I guess, Norm, do you want to say more about the exercises? All right, I'll hand it over to you.
I can't see what's on the screen. Can you guys see my screen, or is it shared properly?
Yes, we're seeing your screen.
Okay. So good morning, everybody. I hope everybody's having a good time. So the lab today should be in two parts. One is the VQE part, which I've hopefully designed to be very straightforward and easy to go through and get familiar with Qiskit a little bit. Hopefully most people at the summer school have used at least one of the different packages out there previously just to get a handle on things. But if not, this is a pretty decent introduction. That being said, if you've never used any of these packages before, either PyQuil, Qiskit, OpenFermion, you might have a lot of questions, and that's why Sohaib and I are here to help supervise. The two things that you see on my screen are the two tutorials that you'll be playing with today. One is called VQE Updated, so I made some changes last night just to fix a couple typos. That's why it's updated. And then there's the Trotter LCU. The VQE Updated is all done in Qiskit. The Trotter LCU is mostly done without PyQuil, but to do the final parts of the exercises, you will need PyQuil installed. So you can do that now, you can do that later. It might make sense just to jump into the Qiskit exercise, get as far as you can go. And if you have enough time, which we're hoping most people will, you should be able to get to the Trotter LCU exercise. As Sohaib said, you will have to install PyQuil, but you won't have to install it right away. You can really just start going into the exercises. If you have trouble with installing PyQuil, you can just jump into the exercises and start going through it. But if you want to make sure everything is working right, do the final test, you will have to install PyQuil onto your own computer. That being said, for the initial exercises, if everything is working correctly, and I've tested with a bunch of different people, hopefully it works just as well in Italy as it does here, you don't have to install anything. I have a README in this GitHub, and you can just click on the link, and you guys should probably start doing this right now. I can't see anybody, but I'm assuming you have or will click on this as I do so. The first part of the README just says go to the Colab website. And this is, so for me, this comes up instantly. If not for you, you'll see a screen like this. You'll want to click File, Open Notebook, and you will be able to just click on GitHub. you'll want to type in my username and Tubman, and you'll want to go to the Colab Summer School. Could everybody do that right now? And if there are any issues, just flag down Sohaib or raise your hand and or touch the screen. I'll try and answer. But everybody should do this now, and I'll wait a minute to make sure everybody's done that. Okay, and if there are any issues, Sohaib is there and he can help guide you. But you're going to want to click GitHub, and then you want to click on VQE Updated. And you should be in the VQE tutorial that we've made for this school. I've made 2 simple examples, maybe not so simple. For some of you, this will be new. For some of you, you might have seen some of this before. But I've made 2 VQE examples. One goes through just a very simple Hamiltonian, a very toy model on 3 qubits at the beginning. And
Norm,
then we
maybe before we get into all that,
yeah.
just a quick check. Can everyone get to this page on Colab?
Yeah, thanks, Sohaib.
Or is there anyone who cannot? You're still working. Okay, maybe let's hold off for a few minutes then, Norm.
Yes. Let's just pause for 2 minutes.
Yeah,
if there are any
let's pause for a
questions,
few more minutes and make sure that folks can make their way to this page.
sure. Why don't you just tell me when you think everybody's ready? That works.
Yeah. Well, I'll do that. And also, I guess this is a good point to check in with the folks online if they're able to follow through. If you can't, please ping us on the chat. Or maybe even a status update of like, who all could make it to this page, and if anyone's running into problems. I'm here to help. If anyone needs any help getting to this page, just raise your hands and I'll come over. And maybe it's worth pointing out that you would also need to sign in to a Google account in order to be able to use Colab. I believe that's correct. Correct me if I'm wrong, Norm.
I've never had to, but that doesn't mean it's not true. I might have some cookies that do it for me automatically.
Okay.
If that's true, let me know. The other thing you can do is, if people have trouble with Colab, you can always download this and install Qiskit on your own machine, and that should work also. But are people having that problem, Sohaib? I mean, most people might have a Google account, hopefully.
Yeah, if you don't and you cannot open the page, please raise your hand.
I don't see anybody in chat. Are things going okay there, Sohaib?
I can't tell. How are things going, folks?
Okay.
Oh, they've already, okay. So you were able to get to that point? Okay. Give it just 2 more minutes, Norm.
Yeah, no problem.
All right, so folks, should we proceed? All right, yeah, I guess go ahead, Norm.
Okay, great. Thanks, Sohaib. So this is the VQE tutorial. You should start here. You should open up the one that's labeled updated. And hopefully I didn't make any more typos, and I removed typos when doing the final updates. This should be what I'm hoping a fairly straightforward tutorial. You will see lots of things in it that introduce a lot of different functionality that you may not completely know. So, at the opening here, you're going to install Qiskit and PySCF through Colab. That won't be done on your own computer. That will be done on the cloud service that Colab is running on. So, we've tested this out. Everything should work very straightforwardly in Colab, even if you might have problems installing on your own computer. That's why we set things up to run in Colab. And that's why the second part is a little bit harder, because you really do need to run PyQuil on your own computer. Should work mostly, but there's always issues when installing things. So that's why we're pretty happy to do things inside of Colab. You'll see blocks like this where I use a lot of different functions in Qiskit. I explain most of them throughout the document. So, don't worry if there are things you don't fully understand at the beginning. They will be explained as you go through the tutorial. That being said, Qiskit is expansive. There's lots of different functions in there. We're not using all of them. There's lots of things that you'd want to explore and investigate if you decide to do more things inside of Qiskit in the future. And you can Google the Qiskit documentation pages if you want to learn how things work in more detail. We try and go through a lot of little things that are useful to getting initial things running here, but for sure in the future, this should be combined with Qiskit documentation in order to do even broader things than what we do here. As I was saying, there's two different things that we do in this initial tutorial. One is I just take a toy model Hamiltonian and demonstrate how VQE works. And then I do a slightly more complicated example, and I import a fermionic chemistry Hamiltonian, and we map it down to the qubits, and we do VQE on that. There are a couple short exercises in here, a little bit of coding to test out various functionality and expanding upon what I demonstrate with VQE. And I've run this through with a couple of the people I work with, and most people have been able to just go through this, at least with the notes available in this tutorial, and finish it without too many problems. So hopefully this will be the easy part of the tutorial, and you'll be able to map this to things that you learned in the sessions in the talks earlier in the day. The second part of this, as I mentioned, is the trotterization LCU part, which I'll open up quickly. I would say in comparison to the previous, the VQE exercises, this one will take you a little bit longer. There's a lot more code to read through. The exercises are slightly more involved. So hopefully for those who finished the first part, you will get here and be ready to go through some very interesting algorithms, which we're hoping that you can pick up and code a little bit here. What I'll say is, I think the first part, the VQE part, should probably take half an hour to 40 minutes if you read through it. And if you get here, I think this will take about half an hour, maybe 40 minutes also. And that should give you guys plenty of time to finish both. There's a lot of people here, so there could be quite a bit of variation in how long things take. So hopefully we've given plenty of time for everybody to finish the exercises. I think Sohaib said he had some more advanced exercises for people who maybe get through these two exercises very quickly. But I think there's plenty here for people to look through and get a feel for how algorithms how they work and can be coded both in Qiskit and PyQuil. So that's where I think I'll leave you here. I definitely think you should start with the VQE tutorial and work up. That was our plan for everybody. I think everybody got to this page initially, which is what we were waiting for. You can just start going through it. I put a lot of text there so people can figure out almost everything on their own. And Sohaib and I are around to answer your questions as you go through it. Anything more on your end, Sohaib? Did I cover everything?
Nothing at the moment.
Okay.
Is everyone good to go? Okay, yeah, so please, start the VQE tutorial. Yeah, do you see a question?
Can I have access to Wi-Fi?
Okay, so we need access to Wi-Fi for the folks.
Could you say that again, Sohaib?
No,
Is there-
that's not a question directed to you, Norm. This is more they need Wi-Fi access.
That hasn't happened yet? Okay.
Well, I guess not for some folks.
Try and plan for everything, but I don't know how to plan around lack of internet access.
Maybe once they make their way through some of the VQE notebook, Norm, you could provide some context, say a bit more about, what efficient ansatz is, what these optimizers are, and so forth.
I think I'll give people about 15 minutes to start reading
Yeah.
through.
Not right now.
Yep.
Once they sort of get into it.
Yep. I think that makes sense. So in about 15 minutes, I will stop people. I'll pull people where they're at, and I'll
Yep.
say a little bit more about what's going on. I think that works well.
Yep, sounds good.
I'll be looking for any questions in the chat. And Sohaib, you should cover the room, and I think that will be an efficient way of doing this.
Please feel free to post questions in the chat. And you can also just raise your hand and I'll swing by.
So I don't mean to interrupt. Somebody posted a question in the chat and I wanted to answer it briefly. On the screen, I have a plot of the difference between linear entanglement and full entanglement. So if you've gotten to the efficient SU2 part of the tutorial, which isn't too far down, I just have people use an ansatz called linear entanglement, which is plotted here on the left. And the full entanglement is also, well, not on the left, but on the top. And the full entanglement is plotted on the bottom. My understanding of this, which things keep changing in different versions of Qiskit. My understanding of this is the difference is how the 2 qubit gates are arranged in the circuit. If you look at the top one, it's assuming a linear geometry, which is to say the 2 qubit gates only can be affecting the qubits that are adjacent to it. So it's as if you have qubits that are in a linear chain. And you only allow 2 qubit gates for nearest neighbors, where, theoretically, and hopefully, as quantum computers evolve, we'll be able to have 2 qubit gates that may not be limited to just nearest neighbors. And if you look at the bottom, these blue things are the 2 qubit gates, the little dot and the bigger dot. Hopefully you've seen these gates before. When they go between nearest neighbors, that means you have a 2 qubit gate between qubit 0 and qubit 1. I hope you can see my cursor, but you can also see in the full entanglement that there's a 2 qubit gate between qubit 0 and qubit 2. This would be impossible in a quantum computer where you're only allowing 2 qubit gates between adjacent qubits, but certainly something that might be possible in the future, depending on the control system. And it's definitely something you can play with theoretically, and Qiskit allows you to set up an ansatz where you can do both types of 2 qubit gates. I hope that answers the question. Feel free to post in the chat if you have any follow-ups. Hi, I think now, Sohaib, you might want to go around, just poll people a little bit, but I think if we give them 5 more minutes, I will say a few words about the first part of the VQE lab, and then I'll just let people go on to the second part. Hopefully a bunch of people have already done that, but let's give them, I think, 5 more minutes, and let me know if you think people have mostly finished the first exercise.
You mean the entire VQE exercise?
No, just the first part of it.
Oh, okay, okay. Yeah. All right. Yeah, 5 minutes sounds good, I think.
I'll pull the
So
people online to see where they're at.
If it was just the first part, Norm, maybe you could talk about it now.
Let me pull people online, see if they've gotten through the first part.
Maybe we can go together as well. Like,
I mean, I going through, like, trying to identify functional ways.
I mean, do you follow, like, I guess what's going on? Like, one of the problems with Qiskit is that, like, it wraps around a lot of functionality, so it sort of hides what's actually happening under the hood, you know, which is which can be helpful, but it can also sort of obscure the details. So I guess Norm will talk a little bit about what's going on, but like, so if you were in Peter's lecture, you know, he talked about variational functionality, and so like, you know, so this is basically setting up a VQ. And the ansatz like tells you like, you know, what sort of structure you're giving to the quantum circuit. The optimizer is like some classical optimizer that you're
Like the structure that he said, like the quantum circuit, the
Yeah.
measure, after that,
Exactly. Yeah.
to calculate the cost of
Yeah.
it, after that, the optimization, and
Yes.
that you change the value. to
Exactly.
update it.
Exactly.
I
Yep.
mean, the general structure, I got it. but-
Yeah. So I mean, you know,
So through that, what I have done, like, put in trying to identify, like,
right. Yeah, this, I mean, you know, because people were doing this, I guess, like so often, and after a while, it sort of gets tedious to set up VQEs from scratch. So I guess Qiskit just set up a VQE wrapper. You know? So
Of course, if you want to change something, you can do it,
Yeah,
and not just
yeah.
take it like.
so once we get to the actual exercise, you know, maybe I can also show you guys like how to actually set up your own, like just kind of using much more primitive operations. Cool. All right.
Okay, so hey,
Yeah, I think Norm, you can go ahead and maybe like explain, you know, some of the stuff in the lab, and I mean, I think folks can run the lab themselves, but it might be helpful to give them more context and. Yep.
so let's do that. And what I'm going to do is, it sounds like most people got to the exercise and they're working on it. And I just want to go through a couple of the main points of what we're trying to look at in this section. And I'd say the broad point is that VQE, it can be messy and can be hard. So can you see my screen? Can you guys see my my collab?
Yes.
Okay, great. So I've run through it. I don't have the exercise here, but I just want to show you a couple of the main points. So we defined a simple Hamiltonian, and this Hamiltonian isn't meaningful at all. It's just a simple example that I know.
We're kind of losing your voice though, Norm.
Okay. How about now?
Yeah, better.
Okay. I'll try and speak up. Just let me know if you lose me again. So we want to define the simple Hamiltonian. We wanted to test out a very simple circuit ansatz, and we wanted to see what would happen if we optimized. And we wanted to do it with semi-real data, right? Like at least numerical data, so we could get a feel for how well things actually work in practice. So if you've gone through the exercise, you'll know that we've implemented this Hamiltonian Qiskit. We have solved for it exactly, which you did close to the beginning, and there should be a line that reads the exact round state. Everybody should have the exact same one since we all ran the same Hamiltonian, so it should be minus 1.414. We defined an ansatz, and we're going to optimize this ansatz with random starting configurations. And I'm not sure if this was covered in the lab, but effectively we're doing nonlinear optimization. We're trying to optimize a complicated function. And for people who know optimization really well, you'll know that when you optimize complicated functions, you will often have a lot of local minima. You'll often be dependent on the starting point. So we have a circuit, we have parameters that parameterize the circuit. When we go to optimize VQE, we'll often do a lot of random starting point for those parameters, because there's no guarantee if we just follow gradients or even non-gradient methods, there's no guarantee we're actually going to be able to find the global minima. We'll often get stuck in local minima. And just as a spoiler for people who played with this and got all the way through the beginning sections, I don't think I've ever seen a local minima for this example. But I wanted to set things up so you could see or have an idea of how to treat things when you do have more complicated problems. For the purposes of this lab, everything has to be done in a certain time period. So I couldn't set up a larger example where things get a little bit more complicated, but that's okay. As long as you understand sort of the basic analysis, how to get started, that was the main point of this lab. So we went a little bit further. We specified an optimizer, and we put in all the information we generated into this VQE function. We set up the optimizer, we picked a random initial point, and we're going to use a state vector simulator, which is the back end for how Qiskit actually runs the circuits.
We're losing your voice again, Norm. It sort of comes in and goes.
I'm doing the best I can.
Yeah, I guess just try to lean in, and it sort of gets better.
Okay. So let me just repeat that last part again. We, up until this point, and hopefully you can see my cursor, we've defined how we want to run a VQE instance within Qiskit. We're telling it what the optimizer is, and there's a bunch of different optimizers. Some are better for noisy simulations. Some are better for classical computers where you don't have to deal with the noise. We're giving it an initial point, which is to say we take the parameters for our circuit and we randomize them to begin with, because we're worried about local minima, even if they're not a big issue for this simple Hamiltonian. And then we give it the state vector simulator. There's lots of different ways in which Qiskit can run the circuit. We're giving it a standard simulator here, but you can do other backends that have different properties, which is out of scope, but Sohaib and I can certainly answer questions on that, at least outside of this or in chat. But going forward, we specified our VQE, and now we're going to run it. But in the tutorial I've given you, I'm actually putting it through a while loop or for loop, and we're going to generate a bunch of different randomness starting parameters and see what happens when we do the optimization. So I did that, and hopefully everybody got to that point. But if not, you'll have time to just continue on through the lab after I finish speaking right now. And you will get a plot that looks like this if you got this far. And you can see the optimizations got to a lot of different points. And that's kind of true and kind of not true. And you can play with that in one of the exercises. Just to make the plot a little bit more clear, I reran it, and this is also in your collab. And I just plotted the energies as a function, or just the different instances. Yours should look similar, but not the exact same as what I have. As I said, we're still using random starting points, and hopefully your random starting points are different than my random starting points. So after you've done all that, I posed a question in the notebook as to why we have such a scatter of different points. And the easiest thing to think of is that there's just a lot of local minima, and we're optimizing to different stable but not global minima for this problem. And I left it as an exercise to investigate that a bit further. And the other explanation, and there might be more even beyond this, but there's two explanations that would come to my mind for this simple example. One is the local minima. The other is I didn't give the optimizers enough time to actually get to the best parameters it can for the different starting positions they have. And you can investigate this more. I'll just give a quick, I don't know how long this will take, but it shouldn't take very long. I'm going to go back up here and change the max number of steps the optimization can do. But before I do that, I just want to relook at this data and see that the scatter, at least in my runs, obviously this is random, but not that random. The scatter of my data here is roughly about 0.1 Hartrees. So, my best values are a little bit under 1.4. My worst values are about negative 1.3. So let me go up and rerun things with, let's just make it 300. So I'm going from 50 maximum steps to 300 maximum steps. I'm going to run the VQE, and then I'm going to, it'll probably take about 30 seconds, but I'm going to let it do the 20 iterations I did before. But this time I'm not going to stop it as early in the optimization. And let's look at the scatter of the energies. So give it a minute, or give it about 20 seconds. All right, we are done, and I'm going to plot the scatter again. And I will sort the points again. And what you'll see here, if you remember before, the range of my values was roughly about 0.1 Hartrees. Now it's, I'm not even sure, it's at least an order of magnitude less in the scatter. And what this tells me is that I wasn't really running into local minima with this onset. The Hamiltonian's really small, the number of qubits is small. It was somewhat unlikely I'd be running into, as many local minima as the previous plot might indicate. I was really just not allowing the simulation to fully converge. So that was, one of the main points of this section. So, a takeaway is you have to be careful when you do your optimization. This was just a simple example, but when you try and let's say you do algorithm development, if you try and run VQE on a quantum computer, you have to start thinking about, are your final results fully converged? What are the different reasons why your final results may not be converged yet? So when you go to harder problems, you start having to deal with both of these issues. If you're to do an 8-qubit or 16-qubit example of a lattice model, or if you start looking at the molecular example in the next section, you might start worrying about whether your ansatz is actually good enough to get you to the ground state. So one of the exercises, and there's a question in the chat, asked what are the layers? So I mentioned that you can run an exercise where you can increase the ansatz. You can increase the number of layers, and that has to do with that efficient SU2 call that was earlier on in the notebook. I'm scrolling up to it. Let's see. So there's this efficient SU2 ansatz here, and there's this parameter in it called rep, which is the number of repetitions of the hardware ansatz. So the general thoughts are, if you take an ansatz or hardware efficient ansatz, you can keep increasing the overall accuracy you can expect out of it by increasing the depth, which means increasing the number of variational parameters. In one layer, you might have 10 variational parameters. If you increase the reps, you'll double that. So you go from 1 layer to 2 layers. Now you have 20 variational parameters. If you set rep equal to 3, now you'll have 3 layers and maybe 30 variational parameters. I'm just giving an arbitrary example, but every layer will have a certain number of variational parameters. And when you do a hardware efficient ansatz, you increase that repetition and you hopefully increase the accuracy or the expressibility of the ansatz that you're looking at. So these sorts of things all become important when you try and do harder problems, which is really what we want to do with VQE. Let's say we eventually get to quantum advantage on near-term hardware with a VQE type of algorithm. Well, you'll want to demonstrate that properly. You'll want to have like an energy that you can believe in that's converged, that actually represents something that you're interested in. You're going to have to deal with the expressibility of your ansatz. Is it good enough to get you to there? You're going to have to deal with local minima. And maybe you get some results and they look bad, but maybe you just got stuck in a local minima and you need to run it multiple times. And you're also going to have to deal with optimization in the presence of noise. And there's even other things I'm not mentioning that can come up as issues when doing VQE. So this exercise represented just a simple example of trying to understand local minima versus not allowing the optimization to finish enough. But when you go to do VQE in practice, either testing out new algorithms you might develop or testing out various models that you want to see how well they perform in VQE, you have to start taking into account a lot of different issues that can arise. So that was the main goal of the first section. Since time is getting somewhat short, Sohaib, can you hear me? Are you still there in the room?
Yeah, I mean, your voice is a bit fuzzy, but I think,
Okay.
yeah,
I'll keep
we can still
picking
hear
up.
you.
But Sohaib, I think there's sort of two things we can do now going forward, or three. People can finish the exercise in this first section. The second thing is people can start going to the molecular VQE section. And the third option is,
we couldn't make out what you just said, Norm. What was the
Okay.
second thing?
Sorry about this. I can write it in the chat or I'll say it one more time. So the first thing is people can finish the first section at their leisure, which would be fine. The second is we can push people to finish the exercise later and start doing the molecular example. And
The molecular
third thing is,
example?
yeah, so that's the second part of the VQE lab.
Okay.
And the third thing is we can just have them start trying the trotterization LCU example.
So I would say, I mean, maybe folks can play around more as necessary on their own. So maybe, Norm, you could walk through the molecular section as well. And then in the remaining time, I can talk a little bit about the trotter and the LCU part. And then, after that, like, you guys can play around with it, like spend more time on whatever, you find more interesting, what you want to get more into. And how about that, Norm?
Yeah, perfect.
Okay.
I'll just spend, so if my audio is coming in and out somehow, you can
Yeah,
just
the
go
audio is
forward.
kind of bad. It's I mean, can sorry?
I don't know if there's anything I can do about that. How about this? If the audio is bad, why don't you just start going through the LCU trotterization? It seems like a perfect time for that.
Okay. Oh, so there is a suggestion about, like, if you face a particular way, then the audio tends to get better.
Say that again.
If you like look away from your screen, strangely. If you look towards the other screen, then it seems to get a little bit better. But okay, yeah, let me I will need
I don't know
to
why.
connect my laptop and I can start walking through the Trotter LCU as well. Just okay, so I'm still opening this in the Google Colab part. Now, unfortunately, the second part of this is something that does require PyQuil, but the first part is something that you could just run in Colab because all it needs is some fairly standard libraries like NumPy and SciPy and some of these things like functools and TQDM hopefully will just come for free. We can just check it out. I think it should work. But while that runs, let me just mention that, earlier today, we talked about the trotterization method, for example, and that's like, the simplest, conceptually, the simplest method for Hamiltonian simulation. And so we're going to, the first part of the lab is just going to be like, seeing this sort of like in action, and we're not going to use Qiskit or anything else. We're actually just going to write our own little quantum simulator in NumPy. And for that, we need a definition of the poly operators. So this is the identity, this is the poly X, Y, and Z operators. And what this function does, the poly 1q operation, it basically says, well, okay, specify one of X, Y, or Z, and tell me which qubit you want that single qubit operator to act on, and tell me the total number of qubits. And this will basically realize the matrix representation of that single qubit operator embedded in the full large Hilbert space. So the way this works roughly is, basically we want, so remember that in these qubit operators are really sort of tensor products of one another. And a tensor product in NumPy you can express as numpy.cron. Cron is for Kronecker product. And so this reduced function, this is like, a nice like technique, I guess, in Python and generally programming. It basically just says like, repeatedly apply this Kronecker function to whatever iterable I have over here. So in this case, I've basically prepared a list that says, have, a bunch of identity gates to the left of the site that you want, your non-trivial operator to be on. Have that non-trivial operator, this is one of, X, Y, or Z, and then have the identities to the right of it, right? And so you just like tensor product all of them, and this is what it gives you. So this should give you a 2 to the n by 2 to the n matrix with precisely the right kind of tensor product, okay? And you can do something very similar with the poly 2 qubit operators as well, right? So here you have to be a little bit careful about like, so now you have to specify which operator you have on site I and site J, and whether I is bigger than J, or, and again, specifies the total number of qubits. So that tells you what this is. The commutator, hopefully self-explanatory, right? So and is just multiplication. This is just matrix multiplication. The spectral norm in NumPy is given by this particular thing. So now we're basically just going to investigate, just look at the effect of like what happens if we actually run this product of exponentials some large number of times for some, single unit of time t equals 1. And so I want to be able to run this for this particularly simple Hamiltonian of just involving 3 qubits. Note that each of these 3 terms fails to commute with each other. So this is, a nice toy example, I guess. And with the helper functions that we just wrote, we can write down each of our Hamiltonian terms. This is, of course, an x0, x1 operation acting on a total number of 3 qubits. So this will be an 8 by 8 matrix, just as, these other 2 terms are also going to be, and the total Hamiltonian is the sum of all these 3 matrices. So now I'm going to explore the effect of increasingly, like, increasing n from 1 to 30, right? And the way I do it is I'm actually doing an explicit matrix exponential of each one of these matrices, right? So XPM is just matrix exponential in Python. And so I'm literally doing like e to the minus I, this first term, times t over n multiplied by, this other matrix exponential multiplied by this other matrix exponential. That defines a single Trotter step. And now this matrix power simply says, like, you know, just multiply that matrix many, many times and many times. So that's all that this is doing. XPAM is actually the matrix exponential of the Hamiltonian itself. So I can always just compute that. If I can compute that numerically, you know, and we can compute it for such a small example, then basically what we're trying to do, so remember that we're interested in basically bounding the difference in spectral norm between this exponential and whatever the thing is on the right-hand side, right? And so that is actually what this thing is computing, the spectral norm of the difference between those two operators. So you just collect those values, and then, you know, you see how that sort of scales as a function of the number of Trotter steps, and you see this kind of nice decrease in error, okay? So the next thing, so what you're asked to explore in this lab, and I will let you do it yourself, which is basically just doing the parts over here, is to do a higher order approximation. So remember when we talked about, you know, the Suzuki higher order formulas, which were, you know, generalizations of these kind of simple product of exponentials. Now we're doing something a bit more clever. So let's call this like the Strang approximation. It's called Strang for historical reasons as well. So now, instead of this product of exponentials, you're asked to basically code this product of exponentials, and then repeat the same steps as you did for before, as you did, you know, for the Trotter case, and you should be able to see a better scaling with, you know, like you should be able to see the error decreasing much faster as a function of the number of steps. So it's a nice, you know, exercise to carry out, and then, you know, if you really want to challenge yourself, I would say go back to the slides. Hopefully you'll get the slides, you know, from the webpage. Look at the, work out what the higher order formulas are, you know, one stage higher than this, and try to see if you get even much better, you know, scaling and so forth. So for the LCU, this is where you will need Pike-Will, and actually there's, you also need at least a slide or two images that seem to be missing here, but since I can't carry this out in Colab anyway, let me try to do the next best thing, which is that I can try and basically give you sort of like, you know, a brief tutorial of Pike-Will itself. Sorry? Yeah, so maybe, you know, folks can start trying out the Trotter. I mean, I just, like, maybe I'll write a very simple variational circuit in Pike-Will, because I think we have like 15-20 minutes remaining, you know. I just want to, like, I mean, you know, because Qiskit gives you some very nice functionality to like actually be very expressive about, you know, the, okay, let's see. I'm just going to call this like, I'm just going to write a very simple program, show you, you know, just how you can write sort of Pike-Will programs like yourself from scratch, okay? So let's start there, okay? And maybe I'll need NumPy as well. All right, so the basic thing that allows you to compose program like circuits in Pike-Will is the program object, okay? So I need to initialize the program object, and basically the program, as the name implies, is just a quantum program. It lets you build up your quantum circuit. So for example, if I wanted to create a Bell state, I would simply compose this program with something like, you know, H0, which is the Hadamard operation, followed by a C0, you know, with 0 as the control qubit and 1 as the target qubit. You can print out and actually see what this program looks like, right? And This spits out what we call QUIL. So QUIL stands for Quantum Instruction Language, and the pi in PyQuil just stands for Python QUIL. It's just a Python wrapper around QUIL, okay? You can use something called a wave function simulator. The wave function simulator is just something that lets you sort of, simulate the wave function directly. You can also run things on, a simulated quantum computer, in which case you'll run into like, you'll actually simulate like getting shots out from a black box and so forth. But if you just wanted to see what the wave function itself looks like, you can just do something like this. This will give you the wave function object, and you can see that, you indeed get something like a Bell state. Yes, question? Which qubits they apply to. Yeah, and by the way, the convention in QUIL is that the 0th qubit is the rightmost qubit, and then followed by the first qubit is so on and so forth. Okay, so one thing I do want to tell you guys about is parametric programs. So we were talking about BQEs, for example, right? Let me write down a very simple BQE. Okay, so okay, so in PyQuil, we can declare certain variables that we could optimize over. Okay, so let me just call it theta. And I'm going to say it's a, so what this says is that, there's some real valued variable, and there's only one of them. Okay, so in principle, I could make this like a list of several variables, but I'm just going to say it's one of them. Now I'm basically going to say, okay, I'm going to apply, and in fact, like sometimes I can even like skip the, the program wrapper anyway. So now I'm going to apply an RY gate of some unspecified angle theta and apply 0 to it. I'm going to follow that now by a C0 gate. Okay. So let's take a look at what the program now looks like. So what this says is the QUIL is saying basically I've declared some real valued variable called theta, which is totally unspecified. But the variational circuit is basically saying apply RY theta to qubit 0 and then follow that by C0 0 1. Okay, so now I can do several things with this, right? So now I can say, just as before, I can say stuff like, if I give theta some random value, let's say that, I give it some random number between 0 and 2 pi. Oops. This seems to not work. Maybe it leads something like this. Okay, yeah, there we go. So now if I give it just some like random particular value, it's going to spit out, the wave function for that random number. And you can sort of like, play around with this, give theta your favorite value, like, I don't know, np.pi or pi/2 or whatever you want, and see that this works, right? So now how do we actually solve for VQEs, right? So now, let me say that my, a very baby example, but let me say that I want to solve for, a Hamiltonian that looks like, this, okay? Or maybe to make it a bit more interesting, let's say that it looks something like this, okay? So this is basically x0, x1 plus z0, z1. And what I'm going to say is that I want to find the value of theta that minimizes the expectation value of this Hamiltonian. Okay. So this is my Hamiltonian. What I can do is I can define an objective function and make it a function of theta and say, okay, so my expectation is going to be something like, I hope I get the order right, and I guess I need to define these inputs. All right, and sometimes Pike will actually return a complex valued thing. So in this case, I will simply discard. And let's just make sure that this actually is working. So let's say that, we define again, so theta is going to be some random number between 0 and pi, say, right? And program is the same program. And indeed, it does give me, an objective function. So now what I can use, what I can do is like, use some third-party optimization library. One of my favorites, the one that I usually use is SciPy. SciPy optimizes minimize library, right? So you can do something like SciPy.optimize import minimize. And so now here, it looks something like this. And I always have to Google, the exact way to define the input, but let's just take a quick look at it. So now I basically need to input what the function is, what the initial values are, any additional arguments, and also perhaps like a method. And there are some additional, optional inputs that you can provide as well, right? So, but all the main things are specify what the objective function is, which I have specified over here. This is my objective function, right? I need a choice for the initial value of that angle, which again, I'm just going to say is some completely random value. And I need additional arguments. So in this case, the additional arguments that I specify are the program and the Hamiltonian. And what else? So the method is like, there are a bunch of methods that SciPy's optimize offers. These are the actual optimizers, right? So you could implement these if you want yourself, but you can also just use these kind of off-the-shelf optimizers. So I'm going to use my favorite one, which is Kabila. And let's see if this actually succeeds. It does not. Okay, let's see what went wrong. These should be a length or a, maybe it's again complaining about, no. Let's see if this works. It's usually these types of like, no. Okay, well, how about folks start playing around with the trotterization lab or part of the lab while I try to figure this out. Okay, so let me go back to just this objective function, right? So all this is doing is that it's taking the program that we defined, which looked something like this, just an RY of some unspecified angle theta acting on 0, followed by a C0 0 1. And we also specified this particular Hamiltonian over here, which is x0 x1 plus z0 z1. And all that this part is now really doing is that the objective just returns what the expectation value is. And the only reason why I actually define this function is so that I can use SciPy's minimize to wrap around it. And I start off with some totally random choice of for theta. I specified that the classical optimizer that I want to use is the Kabila method, but you can use other optimizers as well. This thing just tells you whether your optimization was a success or not. This thing tells you what the smallest value, or the minimal value of the objective function it actually found, right? And this thing tells you what the optimal parameters were. So in this case, there's just one parameter, but in general, it could be like a list of parameters if your variational circuit has, more than one parameter, as is typically going to be the case, right? So for that choice of optimal parameter, I actually print out what the wave function looks like, and actually, this is actually the correct solution. It's something that looks like the Bell state, except it has kind of this phase difference between the 0, 0 and the 1 state. So it's like up to a global phase, it's like 0, 0 minus 1, 1. And so if you you can do this calculation on your notebook as well. If you compute like what the expectation value of XX plus ZZ looks like in this particular Bell state, then it will come out to be something that's 0, right? Which is basically what this number is essentially reporting. So this is how you can write your own variational circuits as well. One additional quick thing I'll point out about Pikewell is that the polys package, for example, also lets you readily create kind of like trotterized versions of variational algorithms, which can be particularly useful if, for example, we have this Hamiltonian right now. Let me just write down a new program that says, so for term in Ham, well, let me just like print out what the terms look like, right? They're just going to be these like individual poly operators, right? And what I'm going to do is I'm going to say, produce an exponential map function of this term. And I now need to say, like, I can define two different parameters now. Let's say that, the one that exponentiates the first term is gamma, and the one that exponentiates the second term is beta. So now this is a function of, well, okay. Maybe what I should do instead of that is to say that, okay, well, let me just like actually first make it a function of just one variable, gamma, and let's see what this program looks like. Okay, so if you remember what we talked about, basically diagonalizing like the X operator, you remember that in order to diagonalize the X operator, we needed to apply Hadamard's on both sides, right? So this is essentially doing that. But apart from that, it's just doing e to the I theta ZZs, right? Which if you remember, we could do by a C naught 0, 1, followed by an RZ2 gamma, followed by a C naught 0, 1 as well, right? So now if I actually do something like this, instead of this particular program, I actually use two different, variational parameters. I could do something like this, right? So I can say exponential map of term of the first term in the Hamiltonian as a function of gamma, and then exponential map of the first term as a function of beta. And now I should have two different parameters in my variational circuit, okay? And in general, I mean, you can write it out also as follows. So you could say, let me just say that like now gamma is a tuple of two variables, right? And now my program looks something like this, right? So this is convenient when you have like, a family of variational parameters. So oftentimes, like, in variational algorithms, we might have like a basic building block, such as in the Hamiltonian variational ansatz, you might have, the exponentials of all the terms that appear in the Hamiltonian, each with their own particular variational parameter. And that composes one block, right? And so if you want to repeat that block, then you might want to assign like the entire families of angles that exponentiate one term in the Hamiltonian as, a tuple of values. So it's sometimes convenient to like package together the variables, that share some kind of commonality in this way. But otherwise, apart from that, this is generically how you would write a variational program in Quill. It, I believe, roughly works the same way in other quantum programming languages like, maybe Qiskit and Circ. I personally haven't played around with them too much. But under the hood, all the fancy VQE wrappers, like they're more or less doing something like this, okay? So I would encourage you to play around with this a bit more. So you would need the slides to, I guess, like carry out this part of the exercise. It's a nice exercise to do. It basically tells you, like, it implements like the technique described in this particular paper, which basically produces like, arbitrary, like if you just specify what the amplitudes are, then it produces the quantum circuit to actually, output that particular state, which is a pretty useful subroutine, which is often used in a lot of quantum algorithms. So, feel free to explore that. And yeah, I mean, shoot me with any questions. And by the way, like in PyQuil, like, another nice feature is that, so remember we had like several dots in some of the circuit diagrams that we were seeing. So over here, this that can be expressed as like the sequence of controlled statements, right? So this controlled RY basically says that, we're going to apply a controlled RY, we're going to apply an RY rotation on qubit 2, controlled on the values of qubits 1 and 0 being in the 1 state. Now, if you want it to be controlled on the value of, say, qubit 1 being in the 0 state, then all you need to do is apply an X operation before and afterwards, right? Because an X simply flips a 1 to a 0, and then you have to just flip it back. So these are some of the techniques that you can explore in this lab. I think we are over time now, so hopefully that gives you a taste of the sort of stuff that you can use, that you can do with quantum programs. Let me just quickly see what sort of questions there are. Okay, good. Okay, perfect. Yeah, so Lorenzo will, I guess, post the slides on the website, and if not, shoot me an email. I'm at this particular email address, and I'm more than happy to just email them to you, okay?
Yeah, so just send me the slides and I will.
I think I already did.
Okay.
Yeah. All right, so I'll stop there, and, yeah, feel free to, ask questions and as we go along.
Okay, so in addition to Sohaib, maybe also Peter is here. So if you have general questions, specific questions, or general questions on the talks you heard today, please go ahead. Otherwise, you can just catch up with them in the next days. Yeah, there's a question.
So for variational quantum algorithms, when we're looking at minimizing, say, the expectation value of a Hamiltonian, so by getting a do we ever go the other way around? Do we ever look at finding iteratively better lower bounds on the ground state?
No, I mean, the variation principle, I mean, will always give you an upper bound. Like you cannot construct, the Hamiltonian has eigenvalues kind of in principle. You cannot, no state will have a lower eigenvalue than the lowest eigenvalue.
But do like some other map it to a different problem that then finds, do we ever map it to a different problem that then finds upper bounds?
No, I mean, I think basically the variation principle has nothing to do with the quantum computer. So like, based on like Feynman's variation principle, so that like if you write on a variation state and you minimize over all the parameters, it's always an upper bound, because maximum, the lowest energy you can find is if you hit the eigenstate with the lowest energy, with the lowest eigenvalue, and yeah, reformulating the problem, I'm not exactly sure what you mean. Of course, if you look at other, if you change the Hamiltonian, that has a different spectrum.
So I mean, for instance, so mathematically, you might say that anything that gets a higher, so looking within the set of non-valid states, and then so if it's like a boundary of the set of states, you can go downwards or you can go the other way.
Well, so the way I think about it is that the Hamiltonian is right.
Yeah.
And there's a corresponding state. So if you now, you can now, of course, write some of the many others, will mix in state with higher. So by making a superposition of this eigenstates, you can never form a state with an eigenvector with the energy smaller than the whole time. And higher with some probability. Does this make sense, or I can write?
Yeah.
Can I add one thing on to what you said, Peter?
Huh? You can add
Can I
something.
add one-
Sorry.
Can you hear me?
Yeah, I can hear you, Norm.
I just wanted to add one thing. There's
Sure.
one method that's completely divorced from quantum computing, or maybe not, but in the classical world called 2RDM minimization. And that will often give a bound from below because you're trying to build in fermionic constraints. So you're always worried about not sampling quite a fermionic wave function when you do this minimization. So that's one place where it arises. I'm not sure of any other places where you're really bound from below, but that is a method in which you do bound from below. It's not a particularly popular method, but it does exist, and people do look at minimizing.
So is that along the lines you were thinking that you're like writing down states that are not normalized?
Yeah. So and then proving that anything that goes lower must be a valid state. So to go from the other side of the set of things that aren't valid states, and then
we can maybe talk more. Yeah,
So in that case, I mean, you can always divide out by the norm of that state and make it so that, you know, it's always valid states.
Yeah. I mean, in the VQE language, going back to there, right, all the states are, you're starting from a normalized initial state, you're applying unitary. So these are just, you know, you can always expand it in the energy eigenbasis. And so then, you know, it's going to have some coefficient Cn with an eigenvalue En, and all the Ens are larger than the ground state. And so you're going to mix in states with higher energy. So by definition, that state will have an energy eigenvalue larger or equal to the ground state.
The main, I think, like one of the main things you need to keep in mind about VQEs, I guess, is like the minimum, like, let's say, well, first there's the issue of like, is your optimizer actually working? Has it only found a local minimum, or has it actually found the global minimum, right? But suppose even if you did find the global minimum, that's only the global minimum amongst the set of states that are actually expressible through that particular ansatz, which may or may not contain the ground state, okay? And so there's this battle in VQEs, there's like this tension between the expressibility of your ansatz and the trainability of your ansatz. So we talked, I guess, I mean, you know, you had a little bit of exposure to this so-called like hardware efficient ansatz, where the idea is that like you just throw like sort of random single qubit and 2 qubit gates, not completely random because they're very variational and they need to be optimized over. But the idea is that if you run a deep enough with just, you know, layers of single and 2 qubit gates, then more or less you can reproduce whatever quantum state you have in the Hilbert space. That's a very expressible circuit, but the cost that you pay is that that it may not become, that it, you know, it loses trainability. So there's this theorem that shows that, you know, the derivative Whereas very structured variational ansatz, something that like, sort of capture the structure of the problem that you're trying to solve, are a bit more trainable. So the thing in variational, quantum algorithms that you have to try and aim for is like something, an ansatz that's both expressible enough that actually contains the ground states of your problem, but structured enough that it can actually also be trainable.
Doesn't even have to contain the ground state, right? Just want to be able to arbitrarily go
Close and
close arbitrarily to
yes.
That's why it's good, right?
Yeah, exactly. Yeah. So I mean, the idea is like if you're interested in like, for example, approximate optimization, then like as long as you get like as long as you can arbitrarily get close to the ground state, in some controllable, fashion, like if you increase the number of layers or whatever, then that's a good ansatz. Yeah, thank you.
Yeah, so I understand from this real-time evolution that you were showing us earlier, was the motivation there to have a more efficient encoding of Hamiltonian dynamics or this, or?
Right. So again, the idea would be that so in a Trotter circuit, and I didn't show any results, but they're on the slides that Lorenzo uploaded. So if you run a Trotter circuit, it becomes longer and longer as you simulate for longer and longer times. And so you cannot reach long times, if you fix the circuit depth. Whereas for the variation ansatz, in principle, you're just updating the parameters. So you can reach arbitrarily long times as long as your variational state is still being able to track and follow the exact dynamics. So it allows you to simulate for a much longer time. Of course, there's a caveat, which is that under non-equilibrium dynamics, very often the entanglement grows exponentially. And in order to track that state with a sufficiently high fidelity, you need to expand your ansatz and effectively also make it longer. And so that also limits the amount of time that you can do the variational dynamics. But the idea is you can maybe then have an approximate way of the state or so. But I mean, I guess what I said initially is still the motivation that, your ansatz does not become longer. You're just updating the parameters, which allows you to track the system over a longer time.
And in real world examples, sometimes this is favorable.
So I mean, we have done this using this adaptive approach. And so we have studied these questions. So this is on the slides also, like, for example, so how does the number of C0 gates, how does the number of variational parameters scale in the long time limit with the system size? So this depends on the type of Hamiltonian you're simulating. So if you have an integrable model, where you can map it to free fermion, they're different. I mean, if you have an integrable model and you can map it to free fermions, you can actually do this very well. Then you get a very modest growth, like polynomial growth of the number of variation parameters at the final time. And it can even saturate. So we also found it. So as a function of time, the number of parameters saturates. And if you look at the final time of the simulation as a function of system size, it grows either polynomially for these integrable models or it grows exponentially for non-integrable models. So you see for non-integrable models, you cannot go to long times. Yeah? If you have an exponential number of parameters in the system size that you cannot deal with. But so in some sense, right, there is a fundamental flaw that, the models that have a nice polynomial growth are also those that are a bit easier, right? I mean, if you map it to free fermions, you don't need a quantum computer to calculate the dynamics, right? But people still do this, and they can even show how to compress the circuits to constant depth, and the variation algorithm could give you a similar circuit, and you can try to understand this. You can do this using the beta ansatz. So there are some ideas of using beta ansatz to compress circuits, and this adaptive approach, for example, gives us the same scaling as you can show from this beta ansatz compression. But I think in general, there's one thing that I didn't touch on, but I think it's important. And that is that in the classical world, the complexity of a state, of representing a state, is really equal to the entanglement that the state carries. Because if you want to use something like DMRG or tensor network approaches, it's the bond dimension that limits, that limits you. That's the computational cost, and the bond dimension is associated with the entanglement, because that's, Whereas in the quantum world, it is it's not like that. So it's more this, there it is the complexity of the state, like how deep of a circuit you need to run in order to represent the state. And so the complexity does not equal entanglement. And so there is potentially a complexity window where you can create longer range entangled states that you could not create classically. And you can then deal with them on the quantum device. So I can guide you also to some papers where they discuss this. Yeah. So that's kind. I think that is kind of like, I mean, so in some sense you can write on variational states, and I mean, people even like take like tensor network ansatz and write it as a quantum circuit and run it on a quantum computer. You can ask why, but the idea is then the quantum computer, you can basically generate states with a higher bond dimension potentially. So in some sense, a variation state is a very broad statement, right? A tensor network would also be a variational state if you want.
More about that tomorrow.
Okay, great. Yeah,
Thanks.
You're an expert.
Other questions? Okay, so thank you very much. To
Yeah,
everybody.
thanks. These are great questions. Thanks a lot.
And see you tomorrow at 9:30. Again, the slides and the notes will be on the school website. You scroll down, you see a list of speakers. Next to them, you can download the slides. And I think that's where the recordings of the talks will also appear at some point. Thank you. See you tomorrow.
Thank you. See you.